and I welcome everyone to the very first episode of our series Node.js Microservices from Zero to Cloud. Viewers, in this series, we are going to build modern, scalable backend systems from scratch. The same kind of architecture used by companies like Netflix, Uber, and Amazon. But before we start coding, we need to understand one fundamental thing, and that is what exactly are microservices and why they do matter. So viewers, grab your coffee, open your notes, and let's break it down. Let's start with what most of us are familiar with, the monolithic architecture. In monolithic app, your entire project is one big unit. The backend handles authentication, products, payments, and orders, all bundled together. There's one shared code base, one shared database, and one deployment pipeline. It sounds simple, and really it is like that. It is its biggest advantage. But as your application grows, this simplicity becomes a problem. Let's imagine we are running an online store. You push an update to the order module, and suddenly something breaks in the user module. Even worse scenario, every time you want to scale one small part like the product section during a big sale, and you ends up with scaling the entire app. That wastes resources and makes deployment risky. Viewers, in short, monolithic architecture come with several challenges. Over here, everything is tightly coupled, meaning even a small change in one part can affect the entire system. And the deployments become slow and risky because you have to redeploy the whole system every time. Viewers, a single bug can crash the entire application, bringing everything to halt. And scaling specific features independently is nearly impossible. This is where microservices come in, offering flexibility, fast deployment, and independent scalability. Now viewers, just imagine that instead of one massive system, we split our application into small, independent services, each responsible for a single function. For example, a user service handles sign up, login, and authentication only. A product service manages catalog data and inventory. An order service takes care of payments and order tracking. Here, each service is like its own mini application. It has its own database, its own logic, and can be deployed independently. These services communicate over lightweight protocols, often HTTP REST APIs or message queues like RabbitMQ or Kafka. The magic of microservices lies in independence. You can build, test, deploy, and scale each part separately. Different teams can work on different services using different technologies. And if one service goes down, the others keep running. It's like turning a big heavy bus into a fleet of small fast cars. Viewers, microservices bring some of the powerful advantages like scalability, flexibility, faster deployment, fault isolation, and easier maintenance. You can scale the parts that need more power at specific time. For example, just boost the product service during Black Friday. Each service can use the best technology for its job. For example, Node.js for user service, Python maybe for machine learning modules, and Go for the payment modules. Similarly, teams can release feature without waiting for the entire system to rebuild. And if the order service fails, the rest of your system still works. Over here, smaller code bases are easier to understand, debug, and replace. But viewers, keep in mind that microservices are not free from problems. These have few trade-offs like complexity, communication overhead, data management problems, and DevOps overhead. Managing dozens of small services, databases, and connections is too tough. You will need Docker, gateways, service discovery, and logging tools. Services talk over network, which means latency, retries, and failures can occur. Each service having its own database can lead to data duplication and consistency challenges. More services mean more continuous integration and continuous deployment pipelines and more monitoring over cloud. So remember, microservices solve scaling and modularity problems, but they add operational complexity. You replace one big problem with many small manageable parts. Now viewers, here's a question I get all the time. Should every project use microservices? Absolutely not. If you are building an MVP, demo, or a small startup app, or a proof of concept, start with monolithic. It is faster, cheaper, and simpler. But when your system starts to grow, when you have multiple teams, scaling bottlenecks, or a large user base, that's when breaking it into small microservices. A good rule of thumb may be monolithic are quicker to start but slow to scale, and microservices are slower to start and faster to scale. So don't jump to microservices because it's trendy. Use them only when they are really required. Now viewers, let's look at how real companies use microservices. Netflix was one of the first to popularize them. They moved from single Java application to hundreds of microservices to handle millions of users streaming at once. Uber adopted microservices to separate rides management, driver tracking, and payment. Amazon splits its huge monolithic into small services so teams could innovate independently, which became the foundation of AWS itself. These giants did not start with the microservices. They evolved into them as their system grew. That's the same journey we will take in this series. So viewers, to wrap up, monoliths are simple but rigid, and microservices are modular but complex. Choose the right approach for your project size and growth. In the next episode, we'll set up our development environment using Node.js, Express, and Docker. And we will start building our very first service. So don't forget to like and subscribe the channel for the next episode. Thank you. Hello viewers, welcome back to the Node.js microservices from Zero to Cloud series. In the previous episode, we explored the big picture, what microservices are, why they matter, and how they differ from monolithic applications. Today we are getting our hands ready for some real coding. Viewers, before we start building services, we need to set up the perfect environment, clean, consistent, and ready to scale. Let's start with the heart of our setup, Node.js. Node.js is the runtime that allows us to run JavaScript outside the browser, making it perfect for building backend services. In first step, visit nodejs.org and download its LTS version for Windows. The LTS or long-term support version is recommended for stability, especially for production-grade microservices. Once downloaded, go ahead and install it using default options. After installation, open terminal or command prompt to run node space -v and npm space -v. Viewers, if you see version numbers for both of them, congratulations. Node and npm are ready. Viewers, no npm comes built in with Node, but many developers prefer using Yarn, a faster and more predictable package manager. To install Yarn globally, simply run the command npm install global yarn. After the installation, verify it using yarn -v. We will use npm or yarn interchangeably throughout this series. Both work great for managing dependencies in our microservices. When it comes to writing Node.js code, Visual Studio Code is the best editor. It's fast, lightweight, and filled with powerful extensions that make development smoother. Download it from code.visualstudio.com if you haven't already installed it. Once installed, let's grab a few must-have extensions. First of all, ESLint to keep your code clean and consistent. Then Prettier for automatic code formatting. Docker if you will be working with containers. REST client to test APIs directly from Visual Studio Code. These tools help us to maintain clarity and consistency across multiple microservices. Now that we have our environment ready, let's talk about how to organize our code base for multiple services. When working with microservices, it is for sure that your project becomes messy. A clear folder structure helps us to stay organized and scale easily as we add more services. Here's a simple structure we will follow. Each service like users, orders, and products will have its own package.json, routes, and dependencies. The share folder will store code that multiple services might need, like environment variables, error handlers, or database connections. And the docker-compose.yml file will help us to connect everything together later in the series. By keeping each microservice isolated but connected through configuration, we achieve modularity and flexibility. Before we wrap up, let's briefly talk about Docker, an optional but powerful tool for microservices. Docker allows us to containerize each service so it runs consistently across all environments: your laptop, a test server, or cloud. Download Docker Desktop from docker.com and install it. Once verify the installation by running docker --version. Later in this series, we will use Docker to spin up multiple containers, one for each service, and connect them via Docker Compose. Even if you are new to Docker, don't worry. We'll go step by step and make sure you understand how everything ties together. And that's our environment all set up. You now have Node.js, npm, Yarn, Visual Studio Code, and optionally Docker, ready to build your first real-world microservice. In the next episode, we'll start coding our user service, we'll define our routes, connect to a database, and test it locally. If you haven't already subscribed and hit the bell icon, do it so that you don't miss the next episodes. Hello viewers, welcome back to Node.js Microservices from Zero to Cloud series. In the previous episode, we set up our development environment for our first real-world microservice. And now it is time to develop the microservice. This would be a complete backend tutorial, and we will build a full CRUD microservice using Node.js and Express, starting from the basic and going all the way to a practical file-based database system in coming episodes. We begin by understanding how APIs and microservices work. Without any data persistence in the first step, and using simple in-memory data handling by using get, post, put and delete requests along with services route endpoint. In second part of the video, we will add real JSON data persistence in each endpoint where every user you add, update or delete is saved permanently inside a JSON file just like a lightweight database. Throughout the video, you will learn routing, request handling, dynamic parameters, error checking, file reading and writing, and how to test each endpoint inside Thunder Client and Postman. Viewers, this video will also include a step-by-step walkthrough on how to install and use the Postman for testing of any API or microservices. By the end, you will have a fully functional backend that works both in memory and with real saved data, giving you the complete picture of how modern microservices and APIs manage and store information. So viewers, let's begin by creating a root folder for our first service. Let's begin by laying the foundation for our microservices application. We start by creating a main project folder named NodeHack, which will act as the root of our entire system. Inside this folder, we add a new directory called services, where each microservice will live independently. Our first service will be the user service, so we create a dedicated user folder. Inside the user service folder, we will initialize a brand new Node.js project. For that, we simply run the command npm init-y. This instantly creates a package.json file with default settings, allowing our service to manage its own dependencies just like a fully independent microservice. Next, we install the core packages we'll be using throughout this service. We run npm install express no daemon codes. Express will be our main web framework for building APIs. Codes ensures our service can communicate safely with front-end or any other services. And no daemon help us during the development by automatically restarting the server whenever we make changes. Viewers, now we set up a clean and professional structure, a source folder that will help to hold all the core logic. We'll create controllers folder, then data folder for storing JSON or temporary files, but we will keep it inside source folder instead of controller. We also create an app.js file inside the source directory, which will act as entry point for this service. Let's walk through our app.js file. We start by importing Express, the lightweight and powerful Node.js framework that helps us to build APIs quickly. This gives access to all routing and middleware features we will need. Next, we import Cores, a middleware that allows our service to accept requests from other domains or ports, especially useful when our microservices or frontend run separately. Then we initialize our Express application. This app object is the core of our service where we register middleware, route and server configurations. App.use express.json enable JSON body parsing. This means whenever a client sends JSON data, Express will automatically convert it into a JavaScript object we can use inside our route. Now viewers, we will define a simple get endpoint for the root URL. Response.json message sends back a friendly JSON message confirming that our user service is active. It's a quick health check for us or any other service. Now viewers, we choose a port for this microservice. Each microservice in our architecture will run on its own port. App.listen finally start the server. When it's up, we log a confirmation message to console. If you see this check mark message in your terminal, you know that the service is alive and ready. Our basic microservice is ready to be deployed on Node.js server on port 4001. We run the server and open the service in web browser with root endpoint / and our microservice is returning user service is running message which shows that the service is running successfully. After this we will create user routes file separately and will implement all functional routes inside that file. Now viewers, inside userroute.js file we will define all RESTful routes for managing users in memory, including creating, reading, updating and deleting user data using endpoints as get, post, put and delete. So first of all, we import the Express library which is used to create a web server and handle HTTP request in Node.js. Now a new router instance is created. This allows us to define routes like get, post, put, delete modularly. Now declare an empty array users to store user objects. This array acts as in-memory database for the app. Now define a get route at the root path / of this router. When someone requests this route, it responds with current users array in JSON format. Now we define a post route at the root path / to add new user. Request contains the data sent by client in the request body. Create a new user object. id:\date.now generates a unique ID based on the current timestamp. And request.body spreads all other properties sent by the client into the new user object. Push the newly created user object to the users array. Now respond to the client with HTTP status 201 and return the new user object in JSON format. Now viewers, we define a put route for updating an existing user. \:ID means this route expects a user ID as a URL parameter from client side. Extract the ID from the URL and convert it into an integer. Then update the users array for each user. If the user's ID matches the given ID, it merges the existing user object with the new data from request body received from client side. Otherwise, user object remains unchanged. After that, send a JSON response indicating that the user has been successfully updated. Now define a delete route to remove a user by ID. Similarly, this route also expects a user ID as a URL parameter. Extract and convert this ID from the URL. Filter the users array to remove the user with matching ID. In this way, the user will be deleted. Now send a JSON response indicating that the user has been successfully deleted. And viewers, at the end, export the router so it can be imported and used in other files, typically in Express application. Now viewers, inside the app.js file, we import the user routes module and mount it on \users path. So all requests to the \users are handled by routes defined in the user routes.js file. Now viewers, basics of our microservices are ready to be used, and this is the time to test its endpoints. For this purpose, we'll install and use Postman, a popular tool that simplifies working for testing of microservices and APIs. It provides a graphical interface where you can easily specify a type of request like get, put, post or delete. We'll download its 64-bit installer from its official website. After downloading it, we'll run its setup and join it with your valid email account. In my case, I will connect it with my own Google account. Allow its access from your firewall if it pops up. Describe your role to use Postman and continue with the free plan. Set how would you use Postman like for testing and automation of APIs. After that, it will show us its testing dashboard. Viewers, first of all, I am testing post endpoint for creation of new user. I am feeding its endpoint URL and setting the body with desired data to save through this post request. On pressing send button, you can see that data has been saved. In next step, I am gonna fetch this saved user through get request and its subsequent endpoint URL. And you can see it has returned user with ID, name and email which we saved in the previous post request. Now viewers, we will use update endpoint with put request and will slightly change the username in the request body. Upon sending put request, it updates the username successfully. Similarly, you can call delete endpoint to delete a user. Now viewers, for testing inside Thunder client, we will open the Thunder client extension and first of all we will copy get endpoint and open Thunder client, initiate new request. We can see that currently there is no user return through get endpoint, as previously saved user through Postman was not saved permanently and on the server restart it vanished. So we will again use add user endpoint here using post command to create new user. For this, just set the endpoint URL and body with the user details to be saved like name, email, ID, and ID would be generated automatically here. Viewers, you can see that the user has been created with the auto generated ID. Now we will update this ID with 1 and slightly change its username through update endpoint using put command. After this, we will verify user details through get command again to fetch the user details. And at the end, we will also use delete user endpoint through delete command to remove any user. In the endpoint URL, we will use user ID which we want to delete and user with that ID would be deleted on posting that request. Now we are checking the availability of that user through ID and also by fetching all users endpoint. Viewers, again if we restart the Node server and start it from the scratch, there is no user available as we didn't persisted any user through Postman or Thunder client. Now we will save the user permanently. So viewers, let's walk through the file handling to store and load our users data from JSON file. This would give Microservices simple file-based persistent layer for storing data permanently. We will create a user.json file in the data package. We set some default users data in the JSON format with ID, name and email. For reading and writing data to JSON permanently, we create a file in utils package for the file operations. Here we are creating file.js. Inside the file, we begin with importing Node.js built-in file system module. Next, we import the path module. This would help us to build file paths and cross-platform way, ensuring our code works on Windows, Mac OS and Linux. Next, we generate a full path to file that will store our users. We navigate into \data and finally point to user.json. This means our service knows exactly where to read and write user data. Next, we define a function whose only job is to read all users from our JSON file. Then we read file synchronously. The second argument UTF-8 ensures the file is returned as reliable text instead of raw bytes. The result is stored in data. Next, we take that plain text and convert it into JavaScript array or object using json.parse. This is function which our routes will use whenever they need the latest user records. Viewers, next we define a function for saving or updating user data back into the file. Next, we convert the user object into JSON text using json.stringify. The null, to part helps to format the JSON with indentation, making it human readable. Then through write file sync function, we write it synchronously to the same user.json file. This ensures our microservice always persists the latest state of data. And finally, we export both functions through module.exports. This would always allow our route and any other module to easily load users and save updates with just one import. And viewers, you see that how our microservices gain simple persistence. No database, yet just clean, reliable file storage that keeps our data safe between server restarts. In later episodes, we'll replace all this with a real database. But for learning microservices, this is perfect starting point. Viewers know that we have set up our basic file persistence layer through file read and write operations. The next step is to adjust our routes so that they may be used this persistence capability to save data permanently. For this purpose, we are creating different root file other than the user routes which was created for routes without persistence previously. We'll name our new file as persistedUserRoutes.js. Here we start by importing Express so we can create route handlers. Next, we create a router instance. These routers act like a mini Express application dedicated only to user routes. Next, we import our helper function. Read users load data from the JSON file. Write users saves updates back data into the storage. This connects our routes to the file-based persistent systems. Next, we define a route that responds to GET request on /users. Every time this endpoint is called, we read the latest version of all users from the JSON file. Finally, we send the entire user list back as JSON response. Now we define our second route to get users with specific ID. Over here, the endpoint handles URL like /user/5, where 5 would be the user ID. We extract the ID parameter from URL and convert it into a number. Then we load all users from the JSON file and put them in the users list. Next, we search for a user whose ID matches the requested one. If no user exists with that ID, we return a 404 error with a friendly message of user not found. And if the user is found, we send their details back to the client as a JSON response. Viewers, next we are defining a route for creation of new user. This route handles new user creation when a post request is sent to /users. We first load all existing users. Then we build a new user object. If users already exist, assign that next ID. If no user exists, start with the ID 1. Spread the request body to include fields like name or email. Then we push the new user into users list. and then we save the updated list back into JSON file using write users function. Next, respond with HTTP status 201 with the message as user added. This is how we can create a new user and save it permanently into JSON file. Viewers, now we will define a persisted route for updation of an existing user with put command. The route with router.put \ID would handle updation of a user by ID. First, load the current list of users, then extract and convert the incoming ID. Then we locate the exact position of the user inside the array. We have missed this line, but we will correct it here. If the user doesn't exist, we return a 404 message. Merge the existing user object with the new values sent in through request from client side. Save the updated list back to the JSON file, and then send a success message and updated user as a response to client. Viewers, after that we are defining a route for deletion of user permanently using delete command and persistence mechanism. This route deletes a user based on their ID. We extract the ID from the URL. Then we load all users. If no user has that ID, return an error message with user not found. We give it a status code as 404. Otherwise, we remove the user by filtering out the matching ID. Then we save the users list after removing the desired user into the users.json file permanently. And at the end, we return user deleted response to client side. Similarly, we export this router so it can be attached to our main app.js file under \users. So viewers, up till now we have defined all persisted routes. Now we will test them one by one. We will open Thunder client, and after initializing the new request, we use get command to fetch saved users through endpoint URL. It would load already saved users, and you can see two users loaded from the users.json file. Next, we will update the first user through put command, and in its body we will slightly change the name parameter. And viewers, you can see that there is an error in file.js, line number 14. So we'll open the file, and on line 14 we can see that instead of users, it has been typed use sync external store wrongly. We'll make it correct, and will also pass user list as input parameter in the function so that it may handle it. And now upon updating the user, it will update user successfully. Now even after restarting the server, if we again open it in Thunder client and get all users, the updated record of first user is loaded as it have been permanently saved in JSON file. Now viewers, we are creating a new user with ID 3 with name CodingMavrick and email as codingmavrick@example.com. We save it by using post command and create user route endpoint. And now we stop the server and again start it. Upon its start, we again call get all users route, and we can see that the new user with ID 3 is also loaded along with previous users. Viewers, finally we will test the persisted delete user route. For this purpose, we'll use the delete request and its subsequent endpoint URL with ID 3, and when we send this request, the said user is deleted, and if we fetch all users again, it will not load the specified user. We can also confirm it physically from user.json file that whether it has been deleted permanently or not. So viewers, this ends up the today's episode. In today's tutorial, we created complete microservice in Node.js for CRUD operations for user service. We created all necessary packages for a microservice in Node.js. We defined routes in route package for both in-memory data handling and persisted routes for permanent data handling through JSON file. We implemented JSON data read and write operations through read users and write user functions, washed the mechanism to switch between user routes and persisted user routes in app.js file. With this structure in place, our application is ready to grow in modular, scalable way, just like a real production-graded microservice architecture. I hope this video will be helpful for new programmers who are interested in Node.js backend services. Keep watching this series for more exciting stuff and don't forget to subscribe our channel CodingMavrick. Hello viewers, welcome back to Node.js Microservices to Cloud series. In the previous episode, we developed a complete backend CRUD microservice using Node.js and Express. We used in-memory data handling and persistence through JSON database. And today we are going to take our microservices journey one step further by connecting our Node.js service to a real database, that is MongoDB. Where we will start from absolute zero, so even if MongoDB is completely new to you, you are in the right place. We will perform complete installation of MongoDB on Windows and will learn how to use MongoDB Compass. Then we will connect Node.js microservice to MongoDB. We will create a Mongoose model. We will update our route to use MongoDB and will test our microservice on Thunder client. At the end of this tutorial, you will have a fully functional Node.js microservice connected to MongoDB with a complete database persistence, and you will understand exactly how the entire flow works from installation to API testing. So viewers, let's start the journey. Viewers, we will start with the creation of separate package for this user microservice. I am separating its package with the name users Mongo, a bit different from previous package that was users. Now inside the terminal, I will navigate to its folder and will initialize Node project separately for this service through npm init-y command. It will create package file for the project. Now I will install Mongoose, the MongoDB plugin for connectivity of our Node project with MongoDB. Its desired dependencies would be downloaded inside node_module folder. If the project faces Express packages not found error, then also copy Express packages from previous user service and paste inside users Mongo node module. Now inside user Mongo package, create source folder, and inside source folder create another folder config. This folder will carry dedicated db.js configuration file responsible for connecting our microservice to MongoDB using Mongoose. Viewers, we will start by importing Mongoose, which is the ODM library that helps us to interact with MongoDB using schemas and models. This single library allows us to write structured, predictable database code. Now we create a synchronous function named connectDB. Since database operations are asynchronous, this function allows us to wait until the MongoDB connection is fully established. We wrap the entire connection process inside a try-catch block. because connecting to a database can fail for many reasons and we want to handle those errors gracefully. Next we use mongoose.connect along with the MongoDB URL. This is the heart of the file. Here localhost means MongoDB is running on own computer. 27017 is the MongoDB's default port and user underscore service is the database name Mongoose will automatically create or use. The new parser enabled by setting use new URL parser true fixes bugs, improved parsing of special characters and supported SRV URLs. Next, use unified topology true activate the new MongoDB drivers engine that improves server discovery, monitoring, replica set handling and failover logic. Next we log the MongoDB connected message. Then we enter the catch block and here I log an informative error message along with the actual error description. This makes debugging easier by showing the root cause of the failure. Then I would forcibly stop the application using process exit in case of error, because continuing to run the microservice without connected database would cause more errors. This is common pattern in backend apps. Finally, I would export the connectdb function so it can be used in our main app.js file. Now viewers, I will create other necessary packages for our microservice like controllers and routes. Then I will create app.js file inside source folder. App.js file is entry point where our entire microservice is assembled, configured and started. It acts as the main program that Node.js executes to run your service. I will copy the basic code from previous app.js file of our user service and will paste it here. Inside the file, I would shift the user routes object upward in the code for clarity. Moreover, in this file, only two major changes would be made. First, I will import the connectdb, which is database connection function. I will import it from the config/db.js. Next, I will call connectdb function to establish the MongoDB connection. If MongoDB starts successfully, we will see MongoDB connected message, and if it fails, server will exit with an error. And that's it. Rest or things in app.js file are not need to be changed. Now viewers, inside source package, it's time to create model package. Further inside model, create user.js file as a user model. This file defines the structure, rules and behavior of user data inside MongoDB. Moreover, this model acts as a bridge between MongoDB and Node.js application. So viewers, file begins by importing Mongoose, a powerful ODM library. Next, create user schema. A schema is like a blueprint or contract that describes the shape and rules of your data. Here, the user schema defines name as string. Required true means it must exist and we may not skip this field. Similarly, email as string and required true. Now convert the schema into a model called user. A model provides create, find, update and delete user capabilities. It becomes the direct tool used in your routes and controllers to interact with the MongoDB collection. In any Node.js backend, especially in microservices, routes act as the entry point for your service. They define how the outside world communicates with your microservice. Whenever a client wants to get data, send data, update or delete, it always communicates through routes. In our application, previously the user microservice, all our routes were using file-based JSON storage. But now, since we have integrated MongoDB and Mongoose, we need to transform the routes so that they interact with the real database instead of JSON file. These updated routes will now query MongoDB using Mongoose, return real-time database records, save data persistently, handle async operations, give us real CRUD functionality. This makes our microservice production friendly, scalable, and far more reliable than before. Viewers, first of all, I will copy the existing routes from previous user service. Then we'll create file, user routes, and we'll paste routes here. Then I will change get, post, put and delete routes as per new requirements. Now viewers, instead of using file-based read-write functions, I will import the Mongoose user model. This model lets us read, save, update and delete user directly into MongoDB. As this model is inside source folder, so I will modify the path starting from source/model/user. Next, our route handler would be of async nature because MongoDB operations return a promise. A promise in JavaScript is an object that represents a value that will be available in future. When we fetch users from database, it doesn't happen instantly. So JavaScript says, by promise, I will give you data later. That later result is a promise. This does not block the program. It returns the promise immediately and results becomes available later. Async and await are modern JavaScript keywords that make working with promises much easier. Viewers, here by writing async before function, we are telling Node.js that this function will perform a synchronous operation that may be accessing a database or reading or writing files or calling external APIs. Next viewers, instead of reading from the JSON file, we will fetch all users from MongoDB using .find method. MongoDB queries with Mongoose and returns promises. So you need await to pause execution until database finishes the query. Without async, you cannot use await. After that, we'll send this response to client as a list of users. Viewers, next we will implement the route as get user by ID. We will use router.get and /:id along with the use async for database operation. Instead of manually searching in the array, we query MongoDB with user ID. Next, we will return 404 response if user not found from the database. Next, we will return the found user in JSON response. Next, we will start update user route with async db update. We will use find by ID and update function to update the records in MongoDB. We will update the user based on the ID received from the client side and we will keep new as true because by default MongoDB returns the old document. With new true, it returns the updated document. Next, return 404 status with no user found message in response to client in case no user is found for that ID. Next, return the JSON response with the message user updated and the user object. Viewers, last one is the delete user route, which is the simplest one. Just remove the existing logic from the route and apply the async capabilities in the function. Then just use user.find by id and delete with desired id as input, and it will directly delete the user from the MongoDB. If no user exists with that id, just return a 404 error with a friendly message, and at the end return user deleted response to the client. Viewers, now our code implementation is almost complete. If any adjustment would be required, we will do them during the testing. But viewers, before testing it, it's time to install MongoDB on our local machine and run its services. So in this section, we will cover the complete installation of MongoDB, but not in the default location. Instead, we will show you how to install MongoDB in custom drive, for example G drive, and we will learn how to manually set up database and log folders along with adding the MongoDB service if Windows does not add it automatically. Viewers, first open your browser and search for MongoDB community server download. Go to the official MongoDB website and download the MSI installer for Windows. This is the recommended installer because it helps us to set up MongoDB easily through a guided interface. Once the MSI file finishes, double-click to start the installation process. MongoDB will show you the welcome screen. Click Next. Choose the complete setup option. Now instead of installing in default path, we'll change the installation path directory from C to G drive. Click on Change and select your desired drive. Continue the installer and complete the installation. Before starting MongoDB for the first time, MongoDB requires two folders. The DB folder, where all MongoDB data will be stored, and the log folder, where MongoDB writes its logs including startup and shutdown details. Even if you install MongoDB on G drive, we can create these folders anywhere. By default, MongoDB expects them under C drive. So we will create them. Open C drive, create a new folder named data. Inside the data folder, create another folder named DB. Then create another folder named log. Viewers, most of the time MongoDB automatically installs itself as Windows service. But if you do not see MongoDB in the services list, then we can add it manually. To add MongoDB as a Windows service, run the command prompt as an administrator and type the following command. You will see a message saying service created successfully. Now open the Windows search bar, type services and press enter. And you will see that the Mongo service is running in the services. Viewers, after the installation of MongoDB, now start the Node server through terminal. And you can see that there is a DB connection error as use new URL parser and use unified topology are not supported. So as we discussed previously, comment these both parameters from the configuration file. After that, MongoDB will connect successfully with Node microservice. Now viewers, this is the time to test the running microservice through Thunder Client API testing tool. Open it and create new request. And try it for get all users by putting endpoint URL and get command. But viewers, you can see that there is no user loaded. And if we go in the terminal console, there is an error as cast to object ID failed for value 1. Now if we look into the code of get all users out, we can see that there is a little code issue as user.find is a function, but we mistakenly put it as inside the await. You correct it and then run the server again. And you will see that the all users loaded in the Thunder client output response panel. Next we will test create new user route. I will select post command and then set new user values in the body tab. But mistakenly I set underscore id with the value 3, which is wrong, as underscore id is for auto generated id by MongoDB. So I will make it simple id and will send the request. And viewers, you can see that the user is created and you may confirm it from the MongoDB Compass editor. Next we will test the update user route. First get the user details which we want to update. Set the command as put for updation. Now copy its auto generated ID and fit it in the last of endpoint URL and send the command. The user updated message generated, but you can see that its ID has not been changed to 1. So here we will go to the code of this route and change the response code from message to actual user in the last part of the route. But viewers, again if we want to change the ID, there is still a validation error. The thing is, we may not change the ID in this way. So if we want to change the name or email only, we have to skip ID from the body request. In that case, it will save the details. You can test it at your own. But if you want to change users from your own provided user ID only, in that case you have to set ID specifically into your user schema object as a number. There would be a few changes in route also, like change in raw ID value from request object to id:request.param.id, a Mongo query filter object. This object tells Mongoose search in the database for the user whose ID field is equal to 15. So in the code also replace find by ID and update with the function find one and update. This method searches for one document in the MongoDB based on ID, update it with request body and returns the updated document and record. Viewers also include run validators true next to new : true, as run validators true makes Mongoose apply schema validations during update like string or numeric values. Now if we again start the server and test the code, you will see that it would accept ID inside the body and will also update data inside the MongoDB based on ID. But viewers, you can see it is keeping both IDs in the MongoDB. And viewers, in the last we test delete route based on both auto generated ID and user defined ID. Open the request and set the request type as delete. Now set URL with the user defined ID 3 and send the request. It will give an error. Again set the auto generated ID and send the request and it will delete the user successfully. Now viewers, if you want to delete the user based on your own user defined ID, you have to use same strategy as in the update user. So inside the route, change the function from find by ID and delete to find one and delete. Also change the raw ID value from request object to id:request.params.id, a MongoDB query filter object. Now again restart the server, find the user first, then use the delete route to delete it with the ID 1 and you will see that the user is deleted. Viewers, as we wrap up this video, we have now seen how easily we can integrate MongoDB into our Node.js microservice and how easily we shifted from simple in-memory or JSON based storage to a fully scalable database layer. So viewers, today We installed MongoDB, connected it through Mongoose, created our user model, and transformed our existing routes into clean async database powered endpoints, all following real microservices architecture. At this point, your service can reliably store, retrieve, update, and delete data using your own custom IDs, and understand how async and await and ODM methods streamline the entire workflow. If you have followed along, congratulations, you have successfully taken your microservice to the next professional level. In the upcoming videos, we will continue building this system further, exploring powerful techniques like ORMs, raw databases, authentication mechanisms, and many more. Thank you for watching. Stay tuned and keep building amazing things. Hello viewers, welcome to Microservices from Zero to Cloud series. In today's episode, we are going to build a complete order management microservice from start to finish using Node.js, Prisma 7 and PostgreSQL, all inside a clean microservice architecture. Viewers, we will begin by setting up Prisma with the new configuration style. In the first step, we will connect our service to PostgreSQL database and would generate our client. After that, we will walk through each part of database operations, starting from creating new orders, fetching them, updating them, and finally deleting them. Along the way, I will explain how Prisma interacts with the database, how to structure controllers and routes, and how to test everything using real API calls. Viewers, by the end of this episode, you will have full knowledge to integrate Prisma inside a Node.js microservice and to handle database operations through Prisma ORM, a type-safe database layer, instead of using plain SQL queries. So viewers, let's start the learning. First of all, install the PostgreSQL database on your local machine. If you do not have it, go to its official website. I will download its latest version 18.1 by selecting Windows platform. Its latest version will take some time to download, so be patient. After its complete download, run its setup. First of all, it will update Microsoft Visual C++ vDistributables. After that, set the drive where to install it. I have space in G drive, so I will install it in G drive. Select at least PostgreSQL Server and pgadmin from the above section. Rest two options are optional. Set the desired password for PostgreSQL. Try to set some alphanumeric password. Set the default port as 5432 and set the locally as default. Now click the next and it would start installing the database. Viewers, since we have selected installation of Stack Builder, so it is prompting about installation of additional components. I am selecting PG Bouncer and PG Agent as add-ons, and I need all 4 database drivers. Rest I need to work for GIS, so I am selecting to install PostGIS special extension. But viewers, you may skip them. Even if you don't need any of them, you may skip and your PostgreSQL will work fine. Now viewers, for additional drivers installation, setup may again ask you for PostgreSQL hostname, username, password and port. So set it as previously. Now setup will ask for Windows Administrator password. Provide it. And after installing all additional components, finish the installation. Now viewers, it's time to perform real coding. Open the Visual Studio Code and make directory for order service. Navigate inside it and initialize node using npm init-y. It would also create package.json file. Now install the desired dependencies. First one is Prisma ORM. Use the command npm install space @prisma/client. Prisma is an open source next generation object relational mapper for Node.js. Next, run the command npm install space --save -dev space prisma space nodaemon. Viewers, nodaemon is a utility that monitors for any changes in your source code and automatically restart your Node.js application. -save -dev is the flag that instructs npm to list these packages in dev dependencies section of your package.json file and is not required when application is running in production mode. Now run the command npm install express. This is only required when you do not have Express installed on your machine. Now create docker-compose.yml file at the root of the project. Then paste the configuration in this file, including container name as postgres-order-service. Set the environment tag with parameters like postgre user, password, db name as order service, and ports. This file is optional and would be required when we will deploy a project on cloud. Next, viewers, change the package.json file. Set the script tag with dev start prisma migrate and Prisma Studio settings. Now run the command npx prisma space init to initialize Prisma ORM. This sets up the foundational files and configuration to use Prisma for database operations. This command creates Prisma directory, schema.prisma file and .environment file. Viewers, schema.prisma file inside Prisma directory serve as the single source for your database schema. You will define your data models and their relationship in this file using Prisma declarative schema language. And viewers, .env file is an environment file which is created in our project's root directory. It contains the environment variables like database_URL, which Prisma uses to connect to your database. By default, it is often sets up a placeholder connection string for PostgreSQL, which you can modify for your specific database. Now replace the database_URL setting with your own PostgreSQL database string carrying the DB configuration for connection. Now viewers, open the schema.prisma file and create a model named as order, and inside it create fields like ID, order info, items info, and so on. In this model, ID is automatically incremented and order ID is the user defined ID based on own business rules. Whereas item is of type JSON to store complex data structures like an array of products, quantities, prices, or any other field. Viewers, @default sets the default value for status and created at. And in the last @updated at is a special Prisma feature that automatically updates this field value to the current date and time every time the row is modified by an update operation. Now viewers, it's time to migrate our Prisma schema to actual PostgreSQL database. Now use the command npx space prisma space migrate space dev space dash dash name space init. Viewers, this command first of all compares your current schema.prisma file with the actual state of your development database. Then it generates the necessary SQL statements to make the database schema match to your Prisma schema. Then it creates a new timestamped SQL migration file inside the Prisma/migrations directory, tracking the history of changes to your database. Then it applies these SQL changes to the development database. And in the last, it updates the Prisma migrations table in your database to record that the migration has been applied. Viewers, dash dash name space init flag provides a custom human readable name for migration file being created. You can name it anything that describes the changes like create user table or add posts. But init is a common convention for the very first migration in the project that sets up the initial database structure. Now viewers, execute this command. But viewers, you can see that there is an error as missing configuration at prisma.config.ts file or usage of adapter. So we go inside the prisma.config.ts file and change it from default settings. We put the functionality to get parameters from environment file at the top. Then put database underscore URL inside its data source part below the provider. It would get connection string as configuration from .env file. Now again run the migration command, but unfortunately now it's throw the error as authentication failed due to invalid database credentials. So go to .environment file and change the default password from Postgres to 5432 as I set this password during installation. Save the .env file and again run the migration command. And viewers, you can see it has created order underscore service database schema inside PostgreSQL database and has returned the message as your database is now in sync with your schema. Viewers, now open the Prisma Studio using command npx space prisma space studio. Viewers, this is visual database interface that allows developers to easily view, explore and edit data in their database directly through web browser. You can see the simple Prisma Studio interface which shows your schema with all its fields. Data is visualized through it during testing instead of going to PostgreSQL database every time. Now viewers, our database connectivity is almost complete, so we come towards microservice code. First of all, create a source folder and inside it create the main entry point for our microservice, and that is app.js file. Now let's set up the file. At the top we load environment variable using .env and then we bring in express along with course to handle cross origin requests. After that we import our order routes which will contain all CRUD operations for the order service. We initialize our express application, enable course and tell the server to accept JSON formatted request bodies. Next we create a simple health check endpoint on the root path. This is helpful when deploying the service because it lets us verify that the API is up and responding. Then we register our order route under \orders, keeping our route structure clean and modular. Finally, we start the server using the port defined in our environment variables or fall back to 4002 if none is provided. Once the server starts, we log a message so we know our order service is running successfully. Next viewers, let's create the routing layer for our microservice. But first create separate package for it named as routes and then create file order routes.js. Viewers, inside the order routes.js file, we start by importing Express and creating a new router instance. This router will act as a dedicated module to organize all order related routes in one place. We also import the controller which we will build in the next step, and that would control all actual logic for fetching, creating, updating and deleting orders. Viewers, next we define 5 routes. First, a GET request on / to fetch all orders. Then a GET request on / order ID to fetch a single order by its ID. Then a POST request on / to create a new order. Then we use PUT request on / order ID to update an existing order. And in the last, we'll create a delete request on / order ID to remove an order from the system based on order ID. Viewers, each of these routes simply forwards the request to appropriate controller function, keeping our routing clean and readable. Finally, we export the router so it can be plugged into our main app file. Now viewers, let's dive into the heart of our microservice, and that is controller layer. Inside the order controller.js file, we start by importing and initializing Prisma client, which gives us a powerful type-safe interface to communicate with our PostgreSQL database. Viewers, the controller contains 5 asynchronous functions, each responsible for a specific CRUD database operation. First, we export a function called getAllOrders. This function is asynchronous because fetching data from the database can take some time. It receives request and response object, allowing us to handle incoming requests and send responses back to the client. Viewers, inside this function, we start with the try-catch block where the database query will be executed. Using try ensures that if anything goes wrong while fetching data, the error will be caught gracefully without crashing our server. Viewers, at this stage, we are creating the skeleton structure for all our routes in the same way. For each route in the controller, we define the function, set up the try-catch block and handle the error even before writing the actual database implementation. This approach allows us to plan the controller structure clearly and ensures consistent error handling across all endpoints. Now viewers, let's look at the actual implementation inside each function. For getAllOrders, we use Prisma's findMany method to fetch all orders from the database. We apply an order by clause on the created at in descending order so that the most recent orders appear first. Once the data is fetched, we send it back to the client as JSON. Here Prisma.order before findMany shows Prisma is using order model. If model changes like product, then for every query we will use Prisma.product instead of Prisma.order. Next, in getOrderByOrderID, we extract order ID from request.params and use Prisma.order.findUnique to fetch the order with that specific ID. If no order is found, we return a 404 response with the message order not found. Otherwise, we send the order as JSON. This introduces a conditional response based on whether the query returns a result or not. Next, for create order, we destructure the required fields from request.body and validate that order ID, user ID, items and total are provided or not. If any of these are missing, we return a 404 response with the descriptive message. Next, we use Prisma.order.create method to insert the new order in the database. We also provide a default status of pending if none is supplied. Finally, we return a 201 response indicating that order was created successfully along with the newly created order object. Next, in update order, we extract order ID from the request.parent and updated data from request.body. Using Prisma.order.update, we update the existing record inside database. Moreover, where clause is used based on the order ID to identify the record required to be updated. Viewers, payload carries change data sent by client or client app for updation. Prisma.order.update function applies these changes to the database. And viewers, if the order does not exist, Prisma throws a P2025 error which we handle specifically by returning a 404 response. Otherwise, we return the updated order along with success message. And viewers, finally, in the delete order, we extract order ID from request.params and call prisma.order.delete method to remove the order from the database. Like in the update method, we handle the P2025 error for a non-existing order by returning a 404 response. If the deletion succeeds, we respond with the success message and include the details in the deleted order. At this point, our controller is fully wired up to Prisma and ready to power all order related features in our microservice. Now viewers, at this point, we have created all of our routes, implemented every controller function and even successfully applied our database migrations. But before we actually start our service with npm start, there is one more important step we should complete, and that is running the Prisma generate command. So here I will run npx space prisma space generate. Viewers, this command tells Prisma to regenerate the Prisma client based on the latest state of our schema.prisma file. Even though our migrations were successful and the database structure is correct, the Prisma client must also be updated so that our code can use the newest models, fields and relationships. Viewers, now run the start command as npm space start and the server will start with message order service running on the port 4002. But viewers, sometimes with Prisma's default driver, despite of all the steps, there comes an error like Prisma initialization error or Prisma client need to be constructed and so on. In that case of error, there may be another option of connecting with Prisma, and that is through Prisma PG adapter. For this approach, use the command npm space install space @prisma/adapter-pg to install the Prisma adapter. After that, load the environment variable using require.env.config. This ensures that the Prisma and our database connection string can read values from the env file. After that, import Prisma's PostgreSQL adapter, and that is PG package. The reason we do this is because Prisma 5 and above allow us to provide our own PostgreSQL connection pool instead of relying on the default driver. This gives us more control, more stability, and better performance, which is extremely important in microservices. So viewers, now we configure our connection pool. Here we are creating a new PostgreSQL connection pool using the connection string from our .env file. The pool manages database connection efficiently behind the scenes. Next, we pass that pool into Prisma's official PostgreSQL adapter. These steps tell Prisma to use our custom pool instead of default driver. It allows Prisma to communicate through the PG library we have configured. Finally, we create our Prisma client instance using adapter. Now, the Prisma is fully initialized using our pool and our PostgreSQL adapter. This setup ensures proper connection management, better performance, and more predictable behavior, especially when scaling the service and deploying to the cloud environment. With our Prisma client ready, the rest of our microservice code can safely communicate with the database. Viewers, know that our controller is fully implemented and our Prisma client is set up. The next step is to test our microservice and its each route using Thunder Client inside the Visual Studio Code. Viewers, Thunder Client is a lightweight API testing tool similar to Postman, but we built right into the Visual Studio Code, which makes testing super convenient during development. So viewers, let's go through each endpoint one by one. Viewers, we will start with the simplest one, the microservice health check. In Thunder Client, set method to get an URL as localhost port 4002. This hits our default route and will respond the message as order service Prisma is running. Next, we test the post route for the creation of new order. First, set the method to post and set the URL as localhost 4002 orders. Now viewers, inside the body portion of Thunder Client, set the JSON object for new order. This JSON object would carry all the fields information like order ID, user ID, items, total, status with its subsequent values. Over here, items would be a list which carry multiple items or products. After visualizing and setting the JSON object, click the send button. But viewers, it did not save as there was an issue in JSON. Remove the outer brackets as we are passing a single JSON object. Now again click the send button and we can see we have a response message at 201 order created response. Viewers, if any field is missing, you will receive a validation error. Next viewers, we will fetch all orders, and for that purpose we will set the method to get in the Thunder Client and use the endpoint URL as localhost port 4002 orders. Then click the send button and you can see an array of orders returned from the database. If your database is empty, you will get an empty list. Next viewers, let's test fetching a single order by its ID. First of all, there should be get method selected from the request type. Then use the endpoint URL with the order ID as ORD-1001 at the end of the URL and send the command. And viewers, you can see that it has loaded this specific order in the response section. Now viewers, if you want to delete any order, place the ID at the trailing end of the URL like localhost :port/order/order ID. We can place over here too and set the method as delete. No, send the command. But viewers, you can see there is a message as order not found. It is just because we are using order ID for delete condition and we have put simple ID in URL as 2. So place ORD-1002 at the trailing end of URL and send the command. And viewers, you can see that order has been deleted. Now you can even confirm the delete condition from the route controller implementation. And viewers, if order does not exist, you will get a 404 error with order not found message. And now viewers, we will update an existing order using put command, and for that purpose, first of all, get all orders. Then set the method as put. Now copy the details of order from response section and paste them in the body portion. Now inside the body, change the first item name from Coca-Cola to Pepsi. Then put the order ID at the last of URL and click the send command. And viewer, you can see the success message with updated order in the response. Again, you can further update the order by changing its status from pending to shipped and send the update command, and it has changed the order status. Viewers, you can further confirm this change in the data directly from the PostgreSQL using pgadmin. Open the pgadmin and click on the servers and then PostgreSQL. Give the password, then go to databases and then go inside your microservice DB as order_service. Now go inside the schema, tables and order table. Then open query editor to view your data. Now viewers, go to Thunder client and change the second item from milk pack to cocoa milk and send the update command again. Now directly watch the data change effect from pgadmin of PostgreSQL and you can see that it is instantly showing the changed item. So viewers, this ends up the today's session. So let's summarize what we accomplished in this entire session. Viewers, we started by setting up our Node.js microservice structure. Then we moved into configuring Prisma with PostgreSQL using the Prisma default driver and then through Prisma adapter using custom connection pool. After that, we generated our Prisma client, we ran our migrations and connected everything cleanly to our order service. Next viewers, we created the complete route skeleton for every endpoint and built a matching controller structure so that the project stays scalable and easy to maintain. Once the structure was ready, we implemented each controller step by step using Prisma query method like Prisma order.findMany, find unique, create, update and delete. And then we tested all of our API endpoint using Thunder client, confirming that each request and response flow was working exactly as expected. So as a whole, we successfully created a complete microservice for order management system using Node.js, Express, Prisma 7 and PostgreSQL. Viewers, the entire flow from configuration to schema setup, then to client generation, then to controller logic and then to final testing is now fully working and production ready. Viewers, if you find this tutorial helpful, don't forget to like, comment and subscribe my channel CodingMavrick. Hello viewers, welcome to Node.js Microservices from Zero to Cloud series. In today's videos, we will learn how the gateways plays their role in microservices. We will build a full stack serverless mobile enrichment gateway using Cloudflare workers, demonstrating all these API gateways features in action. Viewers, in modern application architecture, especially with microservices, managing how clients communicate with multiple backend services can become complex and challenging. That's where an API gateway comes into play. Viewers, an API gateway acts as a single centralized entry point for all client requests. It handles key responsibilities such as routing requests of clients to appropriate backend service without exposing the internal structure of your system. Gateway ensures authentication and security by verifying client's identity and permissions before letting them access any service. It ensures rate limiting and prevents abuse. It protects services by limiting the number of requests per client or API key. Gateway maintains idempotency and reliability. It ensures that the repeated requests do not cause duplicate operations and maintain consistency across services. Gateway performs response aggregation and transformation by collecting or transforming data from backend services before sending a unified response to the client. Since Gateway handles multiple services, so it ensures robust error handling and monitoring. It catches errors from multiple services and standardizes them to improving client experience. It acts as a microservices decoupling agent and shields clients from internal microservices complexity, allowing service to evolve independently. So viewers, in this video, you will see how the gateway handles authentication, rate limiting, idempotency, and communicates with an upstream MOC provider while exposing a simple, consistent API to the client. So let's dive into the development and see how these concepts are implemented in code. But viewers, before we write a single line of code, it's important to clearly understand the architecture we are about to build. In this project, we'll develop 3 separate systems that work together to demonstrate a real-world API gateway pattern. These systems would be the mobile enrichment gateway, the MOC enrichment provider, and the mobile enrichment client. Let's start with the most important component, the mobile enrichment gateway. This system acts as an API gateway, meaning it serves as a single entry point for all client requests. Instead of allowing clients to directly access backend services, every request flows through this gateway first. This is where we centralize critical responsibilities such as request validation, authentication, rate limiting, idempotency, routing, and response handling. Whereas in real-world systems, this layer is essential for security, scalability, and long-term maintainability. Next, we have the MOC enrichment provider. This represents an upstream microservice or even a third-party API that performs mobile enrichment for the user request. For example, resolving a mobile number, calculating a confidence score, or returning user-related metadata. In production environments, such as a provider could be hosted on completely different cloud owned by another team, exposed as a paid external API, or even implemented as a legacy system. For this project, we will simulate the provider using Cloudflare Worker. This keeps the setup simple, fast and cost-free, while still behaving architecturally like an external microservice. Finally, we have the mobile enrichment client. This is a lightweight web application that represents any consumer of API, such as a mobile app, a front-end web application, or an internal dashboard, or even another backend service. The client's responsibility is intentionally minimal. It collects user input, sends a clean JSON request to the gateway, and displays the response. The client does not handle authentication, rate limiting, provider selection, or error mapping. All of that logic is centralized inside the API gateway, exactly where it belongs. This separation of responsibilities is exactly what makes API gateways so powerful in modern distributed systems. With this architecture in mind, let's start building each component step by step, beginning with the API gateway because everything else depends on it. First of all, we create project structure as mobile enrichment gateway. Now from terminal, browse this package and install node dependencies using npm install-y. This created the package.json file of this project. The second step is setting up our Cloudflare worker and its development environment. Cloudflare worker gives us a globally distributed serverless runtime that is perfect for building lightweight API gateways. To work with workers locally and deploy them to Cloudflare, we use a command line tool called Wrangler. Now install Wrangler using command npm install -g Wrangler. Once Wrangler is installed, we authenticate it with our Cloudflare account. This allows Wrangler to create, deploy, and manage workers under our Cloudflare account. After logging in, we generate a new worker project for our mobile enrichment gateway using command npx wrangler generate maverick mobile gateway. My worker on Cloudflare is slightly different from VS Code worker project, but you may keep both names same. Now it is asking for Cloudflare package. Proceed with yes. Select the directory of root project. Then select hello world example. Then select worker only. Now select language as JavaScript as we are using Node.js project. Now it has started creating the project. Proceed with yes for Git version control. Select deploy your app with yes and deploy the initial hello world worker project. But viewers, you can see that it has not uploaded the code on GitHub as repo is not created yet over there. First create repo, link it with our code and push the code. But viewers, you can see on the GitHub web display code is not uploaded. Issue is that we have executed git add command for write inside mobile enrichment gateway package. But at that root path, there is no code except package.json file. So it was pushing nothing. Basically, Wrangler created the project code inside Maverick-mobile-gateway, another folder inside the root folder. So we shift the code from Maverick-mobile-gateway folder to the root folder and again initialize Git and all its commands and finally push the code. And it uploaded the code to GitHub now. Now viewers, open the wrangler.json file from the root of the project. Set the variables like worker, provider keys and provider URL. As gateway has to communicate to provider through this URL. Also set worker gateway key so that only authenticated clients may communicate through this gateway. Now that our architecture is clear, let's move into the heart of the system, the API gateway implementation. Viewers, index.js file represents the single entry point for all client requests, where we enforce security, validation, rate limiting, and controlled access to downstream services. Remove execution context CTX from fetch handler function. This function is the main execution points of Cloudflare worker. Every incoming HTTP request passes through this function. Next, we authenticate the client by using an API key sent by client inside x-API-key through header. If authentication fails, the request is blocked before reaching any backend service. Next, we pass the content received through body from client such as first name, last name and address. Now next step is to forward this data to upstream mock. This is where the gateway acts as a traffic controller, routing request to the correct backend service or API. We make a server-to-server HTTP request using fetch from the gateway to the mock provider. This request is completely internal. The client never talks to the provider or API directly. We use the post method here. Next, we define the request headers. We explicitly set the content type to JSON so the provider knows how to pass the request body. We also attach a bearer token for provider level authentication. This is different from client API key. This key secures communication between microservices. Now we send the sanitized client data to the provider. Notice that only required fields are forwarded. This ensures the clean data boundaries and prevents data leakage. Once the provider responds, we pass the JSON response. At this point, the gateway has full control over how this data will be exposed to the client. We intentionally sanitize the provider response before returning it to the client. Only the fields that are safe and relevant for the client are exposed as result. Like here we are setting result with only mobile, confidence and request ID. Then we return it as a JSON response. Viewers, know that our API gateway logic is in place. Next step is to run it locally and see everything in action. Viewers, Cloudflare Worker provides a powerful local development environment through Wrangler. To start the worker in development mode, we simply run the command npx space wrangler space dev. This command spins up a local instance of our Cloudflare worker, simulating the Cloudflare environment directly on our machine. Next we try to call the gateway using curl command from the command prompt, expecting a valid enrichment response. Viewers, however, instead of getting data back, we encounter an error that says could not resolve host. This error might initially look like a networking or DNS issue, but in reality, the gateway itself is working exactly as expected. The real reason for this failure is simple. The upstream mock enrichment provider is not running yet. Viewers, always remember that our gateway is designed to forward requests to an external service. Since the upstream mock provider does not exist or is not reachable at this stage, the gateway cannot complete the request. Viewers, before building a fully serverless enrichment provider, in the first step we make something simple to act as our mock service provider. This mock provider represents an external enrichment API that our gateway will call. In real-world systems, this could be a third-party vendor, a legacy system, or a microservice owned by another team. For now, we will simulate that behavior using a lightweight Node.js Express server. So we create mock-provider-client locally. Inside the root package, create mock-provider.js file. Start by importing Express and create a basic application instance. Next, enable JSON parsing so the server can accept structured request bodies. Then define a post endpoint @/enrich. This endpoint mimics an enrichment service by returning a static but realistic response. It responds with a mobile number, a confidence score, and a randomly generated request ID. Notice that there is no authentication, rate limiting, or validation here. That's intentional. All of those responsibilities belong to API gateway, not the provider. Finally, we start the server on port 3000 and expose the /enrich endpoint. Now install Express and then run the command node space mock-provider.js. At this point, our mock provider is running locally and ready to receive requests from the gateway. Viewers, now copy this provider URL and replace it inside wrangler.json file of our gateway project. Again, restart the gateway with dev space server. Now inside the command prompt, execute curl command again. And viewers, you can see it has returned desired response using complete route of client to gateway and gateway to mock provider. Viewers, we can test the same gateway using Thunder Client, an API testing tool inside the Visual Studio Code. First, create the new request and place the endpoint URL of the gateway. Now inside the header, set x-api-key with name we have placed in the wrangler.json file. Next, set content type in header with the value application/json. Now, in the body section, set the first name, last name and address for which we want to get data from gateway and mock provider. Now viewers, send the command and you can see Thunder Client has fetched the desired data from the gateway. Now viewers, this is the time to deploy the gateway again on Cloudflare by the command npx space run space deploy. And you can see the online cloud URL of our gateway as https /Mavrick space mobile dash gateway dot shafqatgreat dot worker dot dev /. Before moving forward with testing of gateway deployed on Cloudflare, it is important to understand why we need a separate mock enrichment provider deployed on the Cloudflare itself. In fact, our API gateway is running as a Cloudflare worker, which means it executes inside the Cloudflare's global edge network, not on the local machine. Because of this, a locally running mock service cannot be reliably accessed by the gateway once it is deployed or even during the edge-based execution. In real-world architectures, API gateways rarely talk to local services. Instead, they communicate with upstream systems that are publicly reachable, often hosted on different clouds, owned by other teams, or exposed as third-party APIs. To accurately simulate this production reality, we create a mock enrichment provider as a separate Cloudflare worker. Viewers, this would give us an online globally accessible upstream service that behave exactly like a real external microservice, but without cost, complexity, and external dependencies. Viewers, by hosting both the gateway and the mock provider on Cloudflare worker, we ensure proper network visibility, realistic request flows, and true demonstration of API gateway concept such as service delegation, authentication, forwarding, and response normalization. For this purpose, create a package as mock-enrichment-provider. Now run the command npx space wrangler space init for creation of Cloudflare worker. Next, click OK to proceed with the Create Cloudflare package. Now specify the directory in which install the worker. That directory name would also be the name of the worker. Just press enter and it will pick the working directory. Now select the template as worker only and language as TypeScript, a bit different from the gateway worker in which we use JavaScript. Now it has started installing dependencies. Now viewers, specify the provision of Git version control as yes. It will create a local Git configuration for the code. Now select the No option to deploy the worker. We will deploy it after completing its code. Viewers, you can see that Wrangler has created complete worker project for out provider. Now go inside the index.ts file. Over here, we start by exporting a default object that defines the fetch handler. This fetch function is the entry point for every HTTP request coming into this worker. Next, we parse the incoming request body. In real system, this would contain user details such as name, address sent by the API gateway. In this mock provider, we do not validate the input deeply because our focus here is on simulating a response, not enforcing business rules. Now comes the core of the mock enrichment logic. Instead of calling a database or an external system, we generate a synthetic enrichment response. We generate a random Pakistani style mobile number to simulate a resolved mobile identity. Then we attach a fixed confidence score. In real system, this confidence would be calculated using machine learning model. Then this response is returned as JSON, just like a real third-party API. The satisfies exported handler class is a Cloudflare provider TypeScript safety check. It ensures our worker fully complies with the Cloudflare expected handler, giving us compile time validation without affecting runtime behavior. It is not executable logic. It is purely a TypeScript type safety feature and you can omit it. Now deploy this mock-enrichment-client using command npx space wrangler space deploy. And viewers, you can see it has deployed the provider worker and returned the URL which we will use in our gateway. Now viewers, copy that provider URL and replace with local URL for provider underscore API underscore URL in the wrangler.json file. Now again restart local gateway worker. Now viewers, open the Thunder client and call the local endpoint URL of gateway. Set the headers with x-api-key and the content type. Now inside the body, put the user first and last name along with address to find mobile and other data from provider service. Now send the command and viewers, you can see gateway has returned the mobile number and other details. You can match them with the provider code. Now viewers, we will implement the core features of the gateway in a modular architecture, making it clean, maintainable and scalable. Viewers, by organizing our gateway features into a configuration file and a separate middleware modules, we can achieve a clean architecture. Each module focuses on a single responsibility like authentication, rate limiting, and later input validation and enrichment logic. This makes the code easy to maintain, test, and extend as we added more feature to the gateway. Moreover, we will organize our code into separate files and folders, so each responsibility of the gateway is isolated and easy to manage. In the first step, we create a configuration folder to hold global configuration and constants. Inside this, we add a constant.js file. This file will store critical variables such as worker API key and rate limits that will be used across the multiple modules. Next, we create a middleware folder inside our source directory. This folder will contain all reusable gateway logic such as authentication and rate limiting. By isolating middleware, we ensure that our gateway can handle cross-cutting concerns efficiently. Now inside the middleware folder, we create auth.js file. This module is responsible for validating incoming requests using API key. Here, we import our constants and define the authenticate function. It reads the x-api-key header from the request, compares it with the value in the constant.worker underscore API underscore key and returns true if the key is valid or false if it is invalid. This ensures that only authorized clients can access the gateway. Next, implement the code inside ratelimiter.js file. This module ensures that no client exceeds the maximum number of requests per minute. We use a map object to track each client's request count and the start time of the current window. The rate limiter function checks the current time and compares it with the start of the rate limit window. If the time window has passed, we reset the count. Otherwise, We increment the count and return true if the request is allowed. If the limit is exceeded, it returns false, preventing further requests. This prevents abuse and ensures fair use of API. Viewers, next we implement idempotency in our mobile enrichment gateway. Idempotency ensures that repeated requests with the same unique identifier do not result in the duplicate processing. This is critical for APIs that handle sensitive data or challengeable operations as it guarantees safety and consistency. We create a new module called idempotency.js inside our middleware folder. This module will manage the storage and lookup of request IDs and their associated responses. First, we declare a map object named requestMap. This will serve as a temporary in-memory store to track requests and their processed results. Next, we define the check idempotency function. It accepts a request ID as input. If the request ID is missing, it returns null, indicating that no prior request exists. If request ID is already present in the request map, it returns the previously stored response, allowing the gateway to reuse the response without calling the provider again. Viewers, to save processed responses, we implement store idempotency. This function takes a request ID and response object. If a valid request ID is provided, it stores the response in request map. Later, repeated requests with the same request ID can retrieve this cached response instantly. Finally, we implement generate request ID. This function creates a unique hash based on the request payload using SHA-256. We first encode the payload as a byte array, then generate a hash using browser's crypto.subl.digest API. The hash is converted to hexadecimal string, which acts as a unique identifier for this request. This approach ensures that each request payload has a deterministic ID. Any repeated request with the same data will produce the same hash, allowing the gateway to detect duplicate efficiently. Viewers know that we have implemented idempotency, authentication and rate limiting. It's time to handle the core functionality of our gateway called the upstream enrichment provider. We encapsulate this logic inside a dedicated service module called enrichmentservice.js to keep our code modular and maintainable. We start by importing constants from our configuration file. This provides us with centralized values such as provider API URL and API keys. Using constants ensures that any future changes required updating only one file. Next, we define an asynchronous function called upstream. It takes environment object and a destructured payload containing first name, last name and address. The environment object allows us to access environment bindings like secrets or service bindings in Cloudflare workers. Next, we set the upstream provider URL from our constants and log it for debugging. Logging helps us to trace requests and verify that our gateway is correctly reaching the provider. Now we make the actual network call to the upstream provider using the fetch API. We provide provider-API-URL, then we send a HTTP method post request to the upstream provider. We include the constant -type header to indicate JSON data and optionally an authorization header if the provider requires it. After receiving the response, we pass it as JSON. Even if the provider returns an error, we attempt to pass the body to capture meaningful error details. Viewers, if the response status is not okay, we throw an error with both the HTTP status and the pass data. This makes debugging easier when the provider returns unexpected results. If everything is successful, we return the passed JSON data to gateway, which will later send it to the client. In case of any network failure or runtime exception, we log the error and throw a generic upstream error. This prevents unhandled exceptions from crashing the gateway. Viewers, by modularizing the upstream call and handling both success and error scenarios, we ensure our gateway is robust, maintainable, and ready for production. Viewers, now we create a utils package, and inside utils we create a module named response.js. This module will centralize the logic for sending HTTP responses both for success and error cases. First, we are defining success function. It takes a data object as input and returns the properly formatted HTTP response with a 200 OK status. We serialize the data object to JSON using JSON.stringify. We set the content type header to application/JSON, ensuring clients know that they are receiving JSON data. Finally, we set the HTTP status code to 200, indicating a successful request. Next, viewers, we define the error function. This function handles all error responses, taking an error message and an optional status code default to 400. We wrap the error message inside an object with the key error and serialize it to the JSON. As with the success function, we set the content type header to application/JSON. The HTTP status code can be customized based on type of error, defaulting to 400 for the client-side issues. Viewers, with this response.js utility, the gateway can consistently send clean and standardized responses, improving code readability and maintainability. Viewers, to ensure our gateway only processes valid requests, we create a small utility module called validator.js. We create it inside the utils package. This module is responsible for checking that all required input fields are present. First, we define a function named validateInput that accepts a data object containing client's request payload. We extract first name, last name, and address from the incoming data object using object deconstructing. This makes it easier to directly check the values without repeatedly referencing data.firstname and so on. Next, we verify that all the required fields are present. If any of the field is missing or empty, the function returns false, signaling that the request is invalid. This allows the gateway to reject the request before making any upstream call. If all fields are present, the function returns true, indicating the request is valid. Viewers, by using validateInput function, we ensure that only complete and properly structured requests reach our enrichment provider, making the gateway more robust and preventing unnecessary upstream errors. And viewers, here our modular project structure is almost complete. Middleware folder contains all middleware tasks like auth.js for authentication, rate limiter for rate limiting, and idempotency.js for idempotency handling. Inside services, we have enrichment service which handles calls to upstream enrichment provider. And utils contains helper fields like validator for input validation and response.js for standardized success and error responses. Now let's look at the existing gateway code in index.js file. Everything is inside a single function. Authentication, validation, upstream calls and responses are all together. We will remove this monolithic code and start rewriting it using our modular structure for clarity, maintainability and scalability. In index.js, we start by importing all the necessary modules, utilities and services that make our gateway modular, secure and maintainable. These include middleware for authentication, rate limiting and all others. In the main fetch handler, we define the entry point for all incoming requests to the gateway. Every request is processed inside a try-catch block, which ensures that any unexpected errors are gracefully handled. The try section will contain the core logic. Meanwhile, the catch block captures any runtime errors and returns the structured error response with an appropriate status code. Now viewers, first of all, we start with authentication. The gateway checks if the incoming request has a valid API key. If authentication fails, an unauthorized error with status code 401 is immediately returned. Next, we implement rate limiting per client. The API key is used to track request frequency. If the client exceeds the allowed number of requests within the time window, the rate limit exceeded error with status code 429 is returned. Then, the gateway passes the request body to extract the client's provided data. Once the data is available, we perform input validation. This ensures required fields such as first name, last name and address are present. If validation fails, a 400 invalid input response is returned. After validation, we handle idempotency. A unique request ID is generated from the request payload. The gateway checks if the response for this ID is already cached. If yes, the cached response is returned immediately to avoid duplicate processing. If no cached response exists, we call the upstream enrichment provider, passing along the client data to get enriched information like mobile number and confidence score. Next, we sanitize the provider response. We ensure that all expected fields are present and safely formatted, including echoing any client provided data back for reference. After sanitization, the response is stored in the idempotency cache. So future requests with the same request ID can return this response without reprocessing. Finally, the gateway returns a successful response to client containing the enriched mobile data, confidence score, request ID and the client's provided input. This completes the full flow of requests through our API gateway. Now viewers, to test gateway in true spirit, we create another simple HTML project with the name mobile-enrichment-client. Then create an index.html file inside it and create all basic input control inside it to get data from client. Now create required CSS file for styling and app.js file for interacting with HTML controls. Now run the HTML file in browser and you can see the basic design of our gateway client test console. Provide the worker API URL and gateway authentication key as we defined in x-api-key. Set the first name, last name and address and click the Run Enrichment button. But viewers, we got course error. So go inside the index.js of gateway project to include imports of course headers as utils/course. Now create a file course.js inside utils package with the following code. Now inside the index.js file create origin as origin request.headers.getOrigin. Also includes course pre-flight check as request.methods options response status 204 and headers as course headers with origin. After this include origin at the end of every message of each modular action such as authentication, rate limiting, validate input, return response section and lastly in the main try catch block. Now go inside the response.js file and import course headers. Next add course in headers of both functions after content-type. After that again deploy the mobile enrichment gateway project. Now again try to send client request to gateway through client app. But viewers, you can see again course error arises. Now go inside the course.js file and add constant allowed origin with origin null and static at the top of the function. After that redeploy the project again and send the same request from client app. Viewers, you can see it resolved the course error but throw the new error as max request not defined. So go to ratelimiter.js file and check the variable and viewers, you can see max request was used but on the definition part it was misspelled as next request. Make it correct and deploy the project again. Now test from the client again and now it throws an error as upstream provider error. Now try to directly call provider through curl command and we can see it is returning data. But when we try to communicate it from deployed gateway project, it is blocking the request. Viewers, upon detailed investigation, it is observed that curls works but worker to worker fails. Provider logs never appears when called through gateway worker. That shows it never invokes. 1042 error means worker route not found. And from Cloudflare suggestions, it was revealed as a known Cloudflare behavior that a deployed Cloudflare worker cannot reliably call another worker using public worker.dev URL. Cloudflare suggests that a worker must talk to another worker using service binding, not a public URL. So viewers, fix the issue of the gateway to provider communication by adding services tag inside the wrangler.json file. Also inside the call upstream function, change the fetch method from URL to env.provider.fetch. Now start the provider logs through nps space wrangler space tail command. Next, set the fields in web client and click the Run Enrichment button. And now you can see it has returned data from mock-enrichment provider. Now viewers, we will test the idempotency feature of our gateway. You can see that on every request by same client, the request ID is changing and idempotency is based on request ID. So every time it is considering it a different request from some different client. In fact, in our code, request ID was auto-generated from client app. To avoid similar requests, so we generate hash request ID based on complete search data sent by client. You can make any other unique logic based on your own requirement. To create hash function, import crypto dependency. Now again send the request and you can see that now request is same for same client. Viewers, now deploy it again online and run the logs through tail command. Now call the enrichment multiple times and you can see log is only returning the gateway log and no presentation of log like received data from the mock provider side, as previously it was doing for every call. Now we can verify it by slightly changing the client request data in the same call and run the enrichment. Now you can see the parameters of the request changed and it fetched the fresh data from the mock provider instead of cached through idempotency. So this testing verifies fine working of our idempotency implementation. Now viewers, we can verify the authentication mechanism of our gateway. The gateway checks if the incoming request has a valid API key or not. For this purpose, just put a key as 123 or anything other than authorized key and run the enrichment. We have got error as unauthorized. Now we put our actual API key for our gateway and we can see that gateway has returned the desired data, which verifies that the working of valid authentication is successful. Now viewers, we will test rate limiting. The API key is used to track request frequency. We set the URL, API key and all other parameters. Now click the Run Enrichment button. It returns the data. Now again click it. It returns the same data. Keep on clicking and you can see that after 5 attempts, it has not returned the data, rather returned a message as rate limits exceeded. It is just because we have set max attempts to 5 in our rate limiter function. Now viewers, test the input validation of the gateway. Just set the gateway URL, then set its API key. After that, set the first name and last name. Viewers, over here do not set the address and keep it empty. Now click the Run Enrichment button and viewers, you can see gateway has returned message as invalid input. This is just because gateway has validated it as invalid or incomplete request. Now fill the address field. This will satisfy the validation requirement and again run the enrichment. And you can see it has returned the valid data successfully. So this justifies the validation of our gateway. And viewers, with that, our API gateway is fully transformed. We started with a single tightly coupled function. Now we have a clean, modular, production-ready architecture. Each responsibility is clearly separated. Authentication is isolated Rate limited has its own logic, validation, idempotency, upstream calls, and response handling all live in dedicated modules. This makes the gateway easier to read, easier to test, and much easier to scale in the future. Every request now follows a clear pipeline. It is secured at the edge, validated for the correctness, optimized with the idempotency, enriched by an upstream provider, and returned in a consistent, predictable format. In short, this is a real API gateway, cloud native, maintainable, and ready for real world traffic. This provides a strong foundation for evolving the gateway with more advanced features over time. Viewers, this video was a bit long with a lot of details, but I hope you have followed it successfully. And if you like this video, don't forget to like and subscribe the CodingMavrick. Hello viewers, welcome back to Node.js Microservices from Zero to Cloud series. Viewers, in modern microservices and API gateway architecture, a single user request does not go to just one server. It actually may travel through multiple systems. For example, a request might go from Cloudflare API gateway to the authentication service, then go to order service, then to payments, then to database or a cache, and maybe even a third-party API. Now here is the real problem. When something becomes slow or broken, traditional logs cannot tell us that where did the request go, which service was slow, where exactly did it fail, and how often is this happening. And viewers, this is exactly where observability comes in. Now, what is observability? Viewers, observability means being able to understand what is happening inside a distributed system just by looking at its outputs. In simple words, it means we should be able to see what is happening inside our system without guessing. Observability is built on three pillars. Logs tell us what happened. Matrices tell us how often and how fast. And traces tell us where a request went. And in a microservices world, traces are absolutely critical. Without tracing, microservices simply cannot survive in production. So viewers, we see what is distributed tracing. Distributed tracing answers one powerful question, and that is, what exactly happened to this specific user request? Viewers, instead of seeing logs from individual services, we see a full journey. For example, we can see something like the API gateway took 120 milliseconds, the authentication service took 40 milliseconds, the database took 20 milliseconds, the order service took 60 milliseconds, and the payment API took 45 milliseconds. This entire journey is called a trace, and each individual step in that journey is called a span. So a trace is the full story and spans are chapters of that story. Now viewers, we look at the Open Telemetry. Open Telemetry, also called OTel, is the global standard for observability. It was created by combining two earlier projects, Open Tracing and Open Census. Viewers, today it is backed by companies like Google, AWS, Microsoft, Meta, Cloudflare, Grafana, and Netflix. Viewers, OpenTelemetry gives us a tracing API to create spans. context propagation to pass trace IDs, auto instrumentation to chapter HTTP database and framework calls, and exports to send data to tools like Grafana. Viewers, OpenTelemetry does not store anything. It only collects and sends data to a backend. Now viewers, we see what is W3C trace context. Viewers, to make tracing work across the entire internet, there is a standard called W3C trace context. It defines two special HTTP headers, trace parent and trace state. These headers travel with every request. So when Cloudflare sends a request to your Node.js microservice, it sends something like trace parent with some ID. This tells every downstream service this request belongs to this trace. This is how all microservices stay connected to the same request. Now viewers, with all this, we find out what is the role of Cloudflare. Viewers, in our architecture, Cloudflare workers act as the API gateway and the root of the trace. It is the very first system that receives the user request. So it must create a trace, attach the trace headers and pass them downstream. That makes Cloudflare the root span of every request in our system. Next, we see what is Grafana. Grafana is the visualization layer. It is what we use to see what is happening. Grafana allows us to search traces, click into span, see latency, see failures, and filter by service, user, or endpoint. Grafana itself does not collect data. It reads from backend like Tempo for traces, Prometheus for matrices, and Loki for logs. Next viewers, what is Grafana Tempo? Basically, Tempo is our distributed tracing backend. It stores trace IDs, spans, timing, and errors. OpenTelemetry sends all tracing data to a Tempo. Grafana then queries Tempo and shows us the complete request flow. And viewers, in the last, we see how everything fits together. So the full pipelines look like this. Cloudflare worker creates the trace. OpenTelemetry collects and propagates it. Grafana Tempo stores it. Grafana UI visualizes it. And now you can debug real production issues. But viewers, why this matters so much? Viewers, without observability, you build microservices. You deploy them, they fail, and you guess. But with observability, you see reality, you debug in seconds, you scale confidently, and you look like a senior cloud engineer. This is what separates junior developers from real cloud engineers. I hope viewers, this video has cleared your concepts about observability. In the next video, we will implement all these features. So don't forget to like and subscribe the channel CodingMavrick. Hello viewers, welcome back to CodingMavrick. Viewers, in today's video, we are starting a new learning series, and that is Learn React from Zero to Cloud. Viewers, before we write a single line of code of React, we need to understand where we stand and where we have to go. So far in our Node.js series, we have learned how to build real backend systems. We built REST APIs, implemented the authentication, then we designed the Express-based microservices. We worked with the MongoDB and we persisted data using Prisma ORM with MongoDB. This means our backend foundation is already strong. Now the next logical step in our learning path is the front end, and that is where React comes in. Viewers, first let's clearly understand that MERN stack consists of MongoDB as a database, Express for backend framework, Node.js for runtime environment, and React as a front-end library. So viewers, up till now we have covered MongoDB, Express and Node.js. And what is missing? That is React. Viewers, React is responsible for everything the user sees and interacts with, like buttons, forms, dashboards, pages, and UI logic. You can think of it like Node.js handles how the system works and React handles how the system looks and feels. Now, let's define React. React is a JavaScript library developed by Facebook for building fast, interactive and scalable user interfaces, especially single-page applications. In traditional websites, the entire page loads, performance is slow and user experience is limited. But in React, only the required UI parts update, pages feel instant, and applications behave like a native app. This is why React is used in modern web applications. Viewers, React follows a component-based architecture. That means we divide the UI into small reusable components. Each component has a single responsibility. Large applications become easy to manage. Viewers, if you already understand functions, services, controllers, then React components will feel very familiar to you. Viewers, before we implement anything, we must understand the core building blocks of React. In this series, we will study components, JSX, props, state, virtual DOM, hooks, and conditional rendering. Viewers, these are not optional topics. They are the foundation of React development. Viewers, now let's connect React with what we already know. In a MERN application, React acts as the client, Node.js acts as the server, and communication happens through APIs. So React sends HTTP requests, it receives responses and updates the UI dynamically. This is exactly why we study APIs properly in our Node.js series. Viewers, React is not just popular, it is industry proven. It is used by Facebook, Netflix, Instagram, Airbnb, and thousands of enterprise and startup applications. Learning React means learning how real-world applications are built today. So viewers, by the end of this React series, you will be able to build modern front-end applications, connect React with Node.js APIs, management of application state correctly, designing of production-ready UI architectures, and you will confidently move toward becoming a full MERN stack developer. So viewers, in the next video, we will set up the React development environment We'll understand React project structure and we'll learn how React applications are organized. So if you have completed the Node.js series, you are ready for this. Hello viewers, in this video we are going to build foundation for our React project. We'll go from a clean slate to a functional React frontend, covering everything from the initial development environment to handling real-time user data. We will cover complete React ecosystem with control components, conditional rendering, hooks, props, and polished loading states. By the end, you will have a UI that is not just functional, but looks and feels like a modern production-ready application. So viewers, let's dive in. Before we start coding, we set up our environment. We are using Vite, the industrial tool for React development, because it's incredibly fast and gets us from code to browser in milliseconds. Viewers, first we ensure that we have Node.js installed on our machine. After that, verify npm package installer. Once both verified, go to extension panel and install ESLint extension by Microsoft. This is used to display linting errors and warning as we type. After that, install Prettier extension. It automatically reformats our code according to a set of predefined rules. Viewers, if you find any issue in preparing this environment, you can watch first video of my series Microservices from Zero to Cloud. Now install Vite from terminal. So run the command npm space create space Vite @latest. Then follow the prompts to give the project name. Then select framework as React and select variant as JavaScript plus SWC. It will generate our project skeleton. Now click the local URL and it is showing default page of our project. Viewers, Vite starts light. It will not install all dependencies. So we will need to go to our project folder and run the command npm space install. It will download the actual React libraries. Finally, fire up again the development server with npm space run space dev. Click the local URL provided and we are officially ready to start the coding. Now viewers, we can see that our basic project structure is okay with node modules in place. Now, as our MERN app grows, dumping every file into one folder will become a nightmare. To build like a professional developer, we need a production-ready architecture that separates our UI from our logic. So for that purpose, inside the source directory, we will create 5 core folders like components for reusable UI pieces like buttons, pages for full screen views like your home or login screen, services to house our API calls to Node.js backend, assets for images and hooks for shared logic. We can create these folders manually in the VS Code sidebar or run a quick make-dir command in terminal inside the source folder. This organization ensures that when our project scales to dozens of files, we'll always know exactly where to find our code. Viewers, now that we are set up, let's clear out the placeholder content and build our custom brand. We are turning the default with landing page into the LiveSphere greeting, working primarily in app.jsx file, the central hub for our application. Viewers, start by opening app.jsx file and clear the existing code. We will replace it with the clean functional component featuring a hero section, a brand heading, and a get started button. Notice how we use a span for brand name. Next, head into app.css. We'll use Flexbox to center our content and apply a modern dark slate background. To make the UI pop, we are styling the Get Started button with React Signature Blue and adding a subtle hover effect to make it feel interactive. Now run the command npm run dev to see the transformation. Viewers, we have successfully swapped the existing component to our custom styled GSX component. This is the foundation of our app visual identity. Viewers, to build a professional application, we need to move beyond a single file. We are transitioning from a basic script to a structured architecture by organizing our logic into dedicated pages and reusable components. First, we'll move our hero section into its own home in source/pages/home.jsx file. This keeps our main view isolated. Over in app.jsx file, we clean the things and now it will act as a manager, simply importing and rendering our home component instead of holding all the HTML. Viewers, next we will build navbar.jsx component. Since this needs to appear on every page, so we will place it in a separate component. In our CSS, we'll use position fixed and add some padding to our main container to ensure our content does not hidden behind the header. This structure is key for MERN applications. While the navbar stays static, home.jsx will eventually handle the heavy lifting like fetching real-time data for our Node.js API without refreshing the entire browser. That's the core of single page application. Now, let's make our navbar permanent by importing it into our main app.jsx. We ensure it stays visible across entire application as users navigate through different pages from this. So, inside app.jsx, we'll import the navbar component and place it as a tag directly above home. In React component tree, app is now the parent holding both navbar and home as its child components. Viewers, since our navbar uses position fix, so it effectively floats above the layout. To prevent it from overlapping our content, we'll head over to app.css and add some padding top to our main container. This pushes the content down just enough to clear the bar. Viewers, placing the nav bar here is a standard production move. It keeps the component mounted, means when we eventually switch between different pages, the nav bar stay rock solid while only the main content area reloads. So viewers, to make nav bar login button functional, we'll use one of the most powerful tools in React, and that is useStates. In a MERN stack application, we often need to show different things based on a user's action, like clicking a button without refreshing the page. We'll create a sample model like a pop-up window that appears when we click login. Viewers, we will create login.jsx file as a standalone component. It uses two props, is open to determine the visibility and on close to handle the exit logic. If is open is false, the component simply returns null, keeping the DOM clean. Back in navbar.jx file, we will import login page. Then inside the component, we create a state variable named as isModelOpen using a useState hook which will control whether the login model is open or closed. We import the useState at the top. We add listener for a click event of login button. When the login item is clicked, we set isModelOpen to true, which opens the login model. After that, we render the login component and pass isModelOpen as the isOpen prop to control its visibility. We also pass an onClose function that sets isModelOpen back to false when the model needs to be closed. Viewers, we will add missing React segments on the function top and bottom. After that, inside app.css, add the styling for login page, including login button and close button for both look and hover effects. Now, to make the look of login page as pop-up container, also add desired model-content styling. Now, again run the server by npm run dev command. And viewers, we can see that login page has been appeared as a pop-up. We may type username and password and then we can close it. Viewers, instead of pulling data from DOM at the last second, React monitors every keystroke and keeps our variables perfectly in sync with what user types. This is done by using states variables. So viewers, inside login component, we create a state variable called username to store the value entered in the username input field. We also create another state variable called password to store the password input value. We import the set state as a hook on the top. Now viewers, inside the input control, we link the value to username state. Whenever the user types onChange updates the username state, the required attribute ensures the field must be filled before submission. Similarly, we link value of password to its state. Viewers, now encapsulate the whole div inside the submit form. Form element listens for the submit event and calls the handle submit function. Now define the handle submit function. Over here, prevent the page from refresh on form submission and just log the username and password in the console. Viewers, to give our app a professional look, we need a loading state. This gives users immediate feedback and prevent them from spamming the login button while waiting for the server. For this purpose, we'll use a boolean state is loading to toggle between text login and spinning icon. We set is loading to true, indicating that the login request has started. Use set timeout to mimic a real network request delay. Once the delay is complete, we log the entered username and password to the console. Now set is loading back to false, stopping the loading state. Make the delay to 5 seconds. Now disable input controls while loading. Do it for username, password and login button also. Now show a spinner if loading is active. Otherwise, display the text as login. Also disable close button while loading. Now go inside the styling files in app.css and add styling for spinner. Viewers, add a @keyframe animation to handle the rotation. Style the spinner with a rounded border and a distinct top color to create that circular motion. This ensures that even if the backend is slow, the user knows that app is working. Now go to login pop-up and click the login button. And spinner wheel rotation started and it disabled alt controls. Viewers, know that we can log in, but we need to land on some other page after successful login. So here we'll build a dashboard. So after the login, dashboard will appear. Viewers, although there are ready-made templates available, but building this dashboard ourselves is more important. It would help us to understand how layout works in React. So first, install the React-Router-DOM, the industry standard for navigation. As after the login, we have to navigate to the dashboard. After the installation of React-Router-DOM, now inside pages, create a dashboard.jsx file. It has a simple sidebar and main content area using CSS grid. Now start by importing React so we can use JSX and create a React component. Then define a functional component named dashboard. Create an ordered list that contains navigation items for the dashboard, including overview section, analytics and settings section. Now inside the app.jsx file, import browser router, routes and route from router DOM to enable client-side routing in our React application. After that, import the dashboard page component. Now remove the default code and wrap the entire application inside the router component, so routing works everywhere in the app. Render the navbar component outside the routes, so it stays visible on all pages. Define the routes container, which holds all routes definitions. After that, create the route to map the root URL to the home component. Then create the route to map /dashboard URL to the dashboard component. Now go inside the login component and import the use navigate route from React router DOM, which allows us to navigate between routes programmatically. Then initialize the navigate function using use navigate, so we can navigate and redirect the user. After that, navigate the user to /dashboard route after a successful login. Now add the basic styling for dashboard component in app.css. Start with the basic layout in dashboard dash container. Use display as flex so that we may easily align our sidebar and main content side by side. Also define styling for sidebar, main content and stats grid. After that, restart the local server with npm run dev command. Now click the login link from navbar. Now inside the login pop-up, set the username and password and click on login button. And viewers, you can see it has started login process, and after 5 seconds it navigated to dashboard page using routing capabilities we implemented. Viewers, you can see our dashboard is hiding behind the navbar. So go to app.css and define the height of dashboard by subtracting the navbar height from the whole window's height. Also add same amount of margin from top to shift the dashboard down. And you can see now our dashboard is adjusted fine inside the browser. So viewers, we have made incredible progress. In just a few steps, we have touched only almost every foundational pillar of React development. Here is the breakdown of what we have covered in LiveSphere project so far. We have covered the components. We built a multi-component architecture. We created app.jsx as the root, navbar.jsx and login.jsx as UI units, and home.jsx and dashboard.jsx as page units. All these are the components. Next, we covered JSX. Viewers, every time we wrote something like return and inside it some HTML code, we were using JSX. We practiced writing HTML-like syntax inside JS. After that, we covered props. We implemented this, then we moved the login model to separate file. We passed isOpen and onClose from parent navbar to child login. After that, we covered states and hooks. We use the most important hook like useState. In navbar, we use state track if the model is open, and in login, we use state to track username and password along with isLoading. We use the conditional rendering to make the UI feel alive. Use the isOpen to show and hide the model, and use the isLoading to swap button content from text to spinner. But viewers, we haven't written any code for virtual DOM, but we have seen it in the action. When we typed in login box and only that specific text field updated without the whole page reloading, that was React's virtual DOM, calculating the minimal changes needed to real browser. So viewers, that was for today, and to finish the React portion of our roadmap, we still need to cover elements like effect hooks, context API and many more. So in the next video, we will cover all these elements. And viewers, if you have liked this video, don't forget to subscribe my channel CodingMavrick. Hello viewers, this is CodingMavrick.